Hey guys, welcome to the video tutorial on how to derive the time-based equations for a simple RC circuit. The equations that we're going to learn how to derive are charge, voltage, and current. Really, I'm mostly going to look at how you get charge, and then we'll talk about how you get the voltage and current. And also I should mention there are other kinds of RC circuits. So when I say a simple RC circuit, I mean one where you've got like a battery, some equivalent resistance, some equivalent capacitance. If there are parallel branches in there, that's a different sort of thing, and we'll learn how to deal with those in a little bit. So on another class day. The starting point for this derivation is this equation right here, which comes to you from Kirchhoff's loop law. So if you move this switch to position B, that would be the charging position. Remember, the idea of an RC circuit is that, if you move the switch to position B, now the battery can start doing its thing, which is pushing current around the circuit. Over time, the capacitor charges up, and the result of that is going to be that current stops flowing eventually in your circuit. Technically, this takes an infinite amount of time for the capacitor to charge completely and for the current to stop completely. But a lot of the time, if you just say a very long time later, we'll assume you're talking about infinity. All right, so where that loop comes, or that loop equation comes from, is just a simple loop following around like this. You've got the EMF of the battery minus IR is the voltage drop across a resistor. And then Q over C is the voltage drop across your capacitor. And the, I guess, nice thing about this equation is that it is correct for any moment for your circuit because it's not about time at all. You couldn't plug in a time value and find out what the current is at some moment. But if you happen to know what the current is at some moment, you could plug in your values and figure out the charge on the capacitor. So the little q here stands for charge at some particular time. All right, now, if you at this point are thinking that you should be able to go ahead and derive this equation right here using what you remember about calculus, then go for it. You can pause the video and do the calculus yourself. And I think that would be a very valuable exercise. If you need to see more, then go ahead. Or if at some point you're like, oh, I see what's going on, then pause the video, go a couple of steps ahead, and see if you come up with it. This right here is ultimately going to be the equation that we're going to get for the charge on a capacitor as a function of time. It starts from this one, and then a few other sort of simple principles, and we'll go on from there. But it starts from this. So if you think you see what to do, then I would say pause and go for it. All right, now, beginning with this equation, if what we're interested in is getting an equation like this one as a function of time, then we need to plug in something into this equation that relates the two things that change over time, which would be charge and current. Because you should probably be able to sort of intuit from this, as the charge goes up, this term gets larger. That must mean the current must go down because this term must get smaller, because at any particular moment, the two circuit elements must be using up the EMF of the battery. All right, so from calculus, you should recall the relationship between charge and current is that current is the derivative of charge. It represents the rate of charge passing through a wire. Okay, so if I sub that in there, the next step is actually, or the next few steps really should look very familiar from the derivations that you may have done with calculating terminal velocity for first order drag. We rearrange the equation, a little bit, okay, and the ultimate goal here being to get Q and dQ on the same side. All right, so this is where that very extra super clever trick comes in of dividing both sides by EMF C minus Q. In case you forgot, this symbol right here is called EMF, for Electro-Motive Force. So that's what that backwards 3 thingy is, in case you may have forgotten. All right, so doing that and a few other things, such as multiplying both sides by dt and dividing both sides by RC, we get this as our next sort of step. All right, well, now all we got to do is integrate. So when we set up our integral, it has to have limits. It must be a definite integral. It can't not be a definite integral. If you try and do it as not a definite integral, then you're not going to get something that actually represents reality. You'll get a totally bogus equation. So it's got to have the limits, because in this case we're starting with an uncharged capacitor, and we want the charge at some particular later time. Okay, so 0 to Q, which is the charge at some random time later, and starting at 0 seconds, going all the way to t seconds whenever the charge is what we're looking for. So those are our limits. The 1 over c is out here, of course, because those are constants. They don't affect how we do the integration. This one is just going to turn into t, and this you should recognize as being something related to natural log. All right, now I couldn't figure out how to get Microsoft Equation Editor to do the bounds thingy, so I've integrated and plugged in the bounds in one fell swoop here. So that's what that is. All right, and then we do that neat little log rule thing where subtraction becomes division. Ooh. Okay, and then the goal was to get charge as a function of time. So now we have to do the algebra, really, just to solve for Q. The next step is that also very clever one of doing E it up, which we will attribute to Mr. Curran. So there we are. We just E'd it up, as it were. All right, multiply both sides by EMF C. Oh, there we go. All right, subtract EMF C and divide by -1 to get Q, not negative Q, on the right side. And boom, factor out an EMF C, and we're finished. That's the charge on the capacitor as a function of time. Okay, now, what about the other equations that you saw? Well, those ones are, well, okay, some of them you get from algebra, some of them you get from calculus. So the voltage on the capacitor is just coming from V equals Q over C, right? That capacitor equation we know. Or really, we wrote it as C equals Q over V, but if you rearrange it, then, you know, it's V is Q over C. So take this equation, divide both sides by C, and that would be the voltage on the capacitor. Getting the current, we go back to this idea that current is the derivative of charge. Well, so if you've got an equation for the charge on the capacitor, take the derivative, and now that's going to be the current through the capacitor as a function of time, which, since the capacitor and the resistor are in series, they're going to receive the exact same current. Okay, I will leave deriving this equation by taking a derivative up to you, meaning please do it. It's a useful exercise. You need to know how to turn this equation, or excuse me, this equation into this equation. All right, so do it as, you know, an additional exercise. But all right, that's current through the resistor. And now the voltage on the resistor, you can get by saying V equals IR. All right, so take this equation, multiply both sides by R, and now you have the voltage on the resistor as a function of time. All right, now that's the equations for charging the capacitor. When you're discharging the capacitor, that would be when the capacitor is charged up to a certain extent, right? And you flip the switch from B to A. So some things are going to change when we do that. So if you, again, want to pause the video and see if you can predict what's going to happen, go for it. If you just want to keep watching, then that's also fine. So when we discharge, you got to remember what's happening is the battery is cut out, right? We flip the switch from B to A, so the battery's gone from the loop, and that means, if you like, the capacitor really now is acting like the battery. Capacitors aren't batteries. They don't provide a constant EMF, but in a lot of ways they do sort of the same thing, right? They do push current around. You can, store up a voltage on them. So they do some of the same things. All right, now, when we charged the capacitor, current was flowing this way, right? There it goes. When we discharge the capacitor, you should note that it will push current in the opposite direction. So current would be going around like this. Okay, so when I write my loop equation over here from Kirchhoff's loop law, I'm using going right as my loop for some reason. I could go the other way, it wouldn't really matter, but that's why the IR is positive and the Q over C is negative. I could have written it the other way. I could have written Q over C minus IR, which would also have worked out just fine. Okay, now, we should remember that I is dQ dt, but see, I've done something funny here. I said that I is negative dQ dt. Well, what's going on there? Well, what is going on is, in this case, the current is representing the rate at which charge is leaving the capacitor. One way or the other, we need to end up with a negative on one side and a positive on the other. So I just arranged things so that that would happen. So more or less, that's why there's a negative sign there. But it should make sense that in this case, it represents charge leaving, so it's negative. Okay, the algebra for these ones is much simpler. Much simpler. Hang on. Okay. Right. Divide by Q, multiply by dt, all that stuff, right? Okay. Integration. Again, limits are required. It's worth noting that the limits are different here. The limits are going from Q naught to Q. It's a different thing, all right? Because the capacitor is starting off charged and, discharging to some charge at some time t. All right, integrating, plugging in the bounds. Again, the algebra for these is much more straightforward. Okay, right, E it up. And there we are at the end. That's the charge on the capacitor. Now, very often, you're not going to really know the charge directly. So, like when we were doing the charging equations, if I want the voltage on the capacitor, which I can actually directly measure with a voltmeter, I can go from my charge versus time equation to my voltage equation by simply dividing by the capacitance. Okay, so if I take Q over C, then that will give me the starting voltage. Now, Mr. Erico, shouldn't this starting voltage here, shouldn't that just be EMF? I mean, not necessarily, only if you actually charge the thing all the way up, but also even then, not necessarily. If we had a different layout for our circuit, as we'll see, the voltage on the capacitor does not have to go to the battery EMF if it's hooked up in parallel to a resistor, as opposed to being in series with it and the battery. So the capacitor voltage does not have to start off as EMF. So very frequently it's more useful to just call the initial voltage on it V naught. Okay, and then the current. Well, if it's the capacitor providing the voltage that pushes the current is just take your voltage on the capacitor equation divided by R, and that will be the current. So the current, as a function of time, when you flip that switch over, is going to be initially at its largest value and declining after that.